Hello, my name is JoeMcMahon, and in this video I'll be talking about the hyperboloid of revolution and how it is constructed and the types of surfaces produced when it is cut by different planes. I'll also explore real-life applications of this shape. Here we have our hyperboloid of revolution. It is created by rotating a hyperbola around its central axis. This produces a curved surface that has an hourglass-like shape, or it can be generated by revolving a straight line about a non-parallel, non-intersecting line as its axis, as shown here on the bottom left. Here in SOLIDWORKS, I created the hyperboloid using the rectangle method. I began by drawing the base circle and the throat circle in plan, which would turn out to be a rectangle in SOLIDWORKS. I bring up the extremities of the circle into elevation and mark off my height to create a rectangle in elevation. I'd mark the vertices of our curve on the throat circle points A and B. I'd extend a line perpendicular from our xy line through point B. In rectangle BCDE, we divide edge CD into a number of equal parts and edge DE into the same number of parts. Join divisions on CD to vertex B, and then join divisions on DE to vertex A. Where these lines cross will give us points on our hyperbola. You either repeat these steps, or in SOLIDWORKS, spline through all our points and then revolve around our axis to create our full shape. When a hyperboloid of revolution is intersected by different planes, it produces different types of curves. These are known as conic sections. The first one we will look at is the horizontal cut. If the hyperboloid is cut with a horizontal plane, the resulting cross-section is a circle. This occurs because the surface is symmetrical around the vertical axis of revolution. You can see this clearly in the SOLIDWORKS section view and the video, as shown in red on the model and in SOLIDWORKS. The second cut we'll look at is the vertical cut. If a vertical plane passes through the axis, the resulting section is a hyperbola. This happens because the hyperboloid itself is generated from a rotating hyperbola. Thirdly, we have angled or oblique cuts. When the surface is cut by an inclined plane, the intersection may produce an ellipse or another curved conic section. Now we're going to look at the applications of the hyperboloid of revolution and where we would see them in day-to-day life. Large power stations often use hyperboloid-shaped cooling towers because they are very strong structures. The hyperboloid's curved surface helps to deflect wind around the tower and help resist damage caused by the wind without the tower bending too much, vibrating dangerously, or collapsing. The shape also helps improve airflow and cooling efficiency inside the tower. Hyperboloid structures are superior in stability against outside forces compared to regular buildings, but because of their curved shape, they often create large amounts of unusable volume and have low space efficiency. Hence, they are more commonly used in purpose-driven structures such as water towers, because they can support a large mass, or for aesthetic architectural builds. And we have an example of each: the Kobe Port Tower in Japan, which acts as an observation deck offering 360-degree view of Kobe, the harbour, and the Rocco Mountains, as well as Cockfoster's Water Tower in North London.